Welcome everybody to the Taiwan Semiconductor webinar about second sourcing rectifiers, and also about how to compare datasheets of rectifiers and time voltage suppressor diodes. My name is Jos van Loo. I'm doing the technical support here for Taiwan Semiconductor, and I'm working in supporting customers across Europe. Let's have an overview about what we're going to talk about today. Cross-referencing rectifiers. Rectifiers are not that often changed once they are designed in on a printed circuit boards. They are exposed to a lot of heat. They do see a lot of high voltages, so they are critical components. But if you look at the Pareto analysis, then actually what you do see is that there are, the failure rate is not very high. So they're not that, critical in most designers' minds. Also, what you do see is that if we're honest with ourselves, rectifiers, they have modest technical innovation. So there's not that much changes in rectifier technology. So people don't really feel the need to change them. So most of the changes come basically commercial, from the supply chain, like in the days of the allocation, or also at the moment with the virus or something like that. There's the supply chain issues. There can be cost savings, and occasionally there are some technical problems. What happens if we run into a situation like that? First, you're going to compare data sheets. You are going to look at your preferred suppliers or do a Google search online, and you're going to compare data sheets. We're going to talk a little bit what can go wrong when you compare data sheets and look a little bit more in details. Then afterwards, I'm going to talk to you about what is actually missing in this data sheet. Is it relevant? What could be, what could be hidden there behind the datasheet values that could still trip you up when you do a cross-reference? We're going to do that for standard rectifiers. And afterwards, we're going to look in a little bit more detail at SCHOTTKY diodes, fast recovery diodes, transient voltage suppressors, bridge rectifiers, and small signal products. The data are available or online. You look at the event boards, that's where the presentation is, so you don't need to make extra notes. You can download the presentation at the end. We can also, at the end, we can also have a Q&A function. For this, you can use the chat function. Then you type in your questions, and I will try to answer them at the end. Here we go, a rectifier or TVS datasheets. What can you see in there, or what information is available? You can always find the absolute maximum rating. You can always see the key electrical parameters, their test conditions, their limits, typical values. You can see the mechanical data. You can see the thermal resistance information, basic curves, dimensions, solder information, and ordering information. Nobody's going to pretend here that a data sheet of a rectifier is very complex. They are the simplest components or semiconductors out there. But you can still go wrong comparing them. And this is what the webinar is all about, or part of the things we try to explain in the webinar. So what can you not see in a data sheet, and for which things you need testing? Obviously, efficiency is difficult to calculate based upon datasheet values. The junction temperature, you better measure, I think. EMI is also something you need to measure. And then behind the datasheet, every semiconductor supplier has different routines or different procedures for testing the product. There's also different process technology that is hidden behind the datasheet. There is a different distributions and CPK values that can actually truncate what you measure rather than just following the datasheet. The real values could be quite different. And then there's difference in the reliability. So two different data sheets can be 100% the same, and one can be a copy of another, but in the actual reality, those two products are never the same, and there are still some difference that you will find once you start buying the product or using it in high volumes. Next slide, the absolute maximum ratings. This is just your average data sheet of a rectifier. There's tens of thousands out there, and they all give you the reverse peak reverse voltage, which is really an absolute maximum rating. So if you go over that 200 or 1000 volts, your part could be destroyed. The reverse voltage RMS value, that's the same thing with the square root 2 division. So it's not really an independent value. The forward current is actually not an absolute maximum rating. We'll talk a little bit more about that. you'll have 10,000 of rectifier data sheets that give you foreign current as an absolute maximum rating, but it really isn't. The junction temperature is. Then the surge current is really an absolute maximum rating. You know, if you exceed that, you will have a digital failure, and you will actually, you know, see failures once you start exceeding that by 10 or 20%. And then, of course, the junction temperature. Talking about junction temperature is a little bit like philosophy. You know, it is a maximum rating and it is not a maximum rating. We'll talk a little bit more in detail about how you can actually look at the junction temperature in different ways. One thing I would like to point out at the surge current here is that it's usually given in a data sheet at 8.3 milliseconds or 10 milliseconds. A lot of designers here will say, why? Well, actually, those conventions are about 30 or 40 or 50 years old, when a lot of linear power supplies were still around. These days, everybody uses switch mode power supplies, and your input surge rating is more in the area of 300 microseconds or 500 microseconds. So this 1 millisecond value is a little bit more helpful for you to judge what type of surge or maximum surge your device will be able to handle. So here we are. We have our two top absolute maximum ratings. There's a huge difference between them. The breakdown voltage is 100% tested in production. So you can actually rely, when you buy a 1000-volt rectifier or 600-volt rectifiers, that actually those values are kept in the data sheet, or actually your actual device will actually meet those values, because they're tested not once, but sometimes 2 or 3 times. The surge current, like if you have a 50 amp or 60 amp surge current, you cannot test in mass production. So it's actually guaranteed by design. So this here, you actually depend on the manufacturer to keep a good process control, have good process control for you to actually be sure that this is 100% functioning in your design. The surge current is determined by the die size. You know, most of the surge currents are under 1 milliseconds, and once the surge current is about 1 or 1.5 milliseconds, the transient thermal impedance is the most important parameter, and the transient thermal impedance is determined by the die size. So actually, if you reduce your die size to save cost, your surge margin may be less good. So you might go from a 30% margin to a 20% margin or 10% margin. So there's a risk there that the suppliers reduce their die sizes. Solder voids are also impacting the surge rating. So if the device has a lot of solder voids underneath the die, then your surge rating might be reduced by 10 or 20% or even more, depending on the size of your solder voids. Some manufacturer introduce a delta VF test to eliminate the biggest solder voids. This is one of those parameters that is actually not known, or you cannot see in a data sheet if a supplier does that or not. You just have to trust the reliability system. The other thing is that on the breakdown voltage, different suppliers have different distributions and different CPK values. So if you're seeing a few spikes in your design, then you might see that different suppliers may give you different margins in your design. The maximum junction temperature. This can be used in several ways. The maximum junction temperature can be used to set the current rating of a rectifier. So the current rating should be such that the junction temperature should not be exceeded. The maximum TJ should also be reflected in the reliability testing results. This is something where really there is no discussion possible. ACQ testing does that for you for automotive parts. So they test the parts at the rated voltage and the rated maximum junction temperature in the datasheet. JEDEC for normal product for commercial parts may have some leniency there, like testing at 80% of the breakdown voltage. But there are actually no rules. So company X can actually determine how they do the reliability testing by themselves, differently from JEDEC or ACQ, to produce their own quality systems and their own maximum TJ. So actually marketing or people can actually influence the maximum TJ in the data sheets. There is no rule that they count. Where the definition of the maximum TJ becomes a little bit more philosophical is when you start looking at ARRHENIUS and field failures. For this, I prepared a slide with, with an extra table of values. What we're talking about now is actually the fit rate, the failure in time rate. Let's say a product has a fit rate of 5, a typical average value for a rectifier. That means 5 field failures in 10.9 or 1 billion device hours. To visualize this, I always say you take 1 million devices and they operate 1,000 hours in 1 year. So you have 1 billion device hours, and the 5 fit means that you have 5 failures in 1 year. Of course, that is at 55 degrees C. So no rectifier works at 55 degrees C. They usually work at a much higher temperature. And here, maybe TVS diodes use at 55 degrees C. There you can actually use that. So let's say your rectifier works at 100 degrees C. Then you use something called the acceleration factor, and the acceleration factor is in the right-hand column. If it's for 100 degrees C, that acceleration factor is 19. You multiply that with the value of at 55 degrees C, and you get a fit rate of 95. So now here you get 95 failures, coming out of your system with 1 million devices and 1,000 device hours. Here is where the definition of the maximum TJ becomes trickier. You can actually go this and multiply this, do this up to 150 degrees C, the maximum junction temperature. There you can look at the difference between 149 and 151 degrees C. Actually, the difference is not that great. 151 is obviously worse than 150, but you're still going to get a lot of field failures. At 150 degrees C, if you multiply 5 by 250, you're talking about more than 1,000 field failures. So you're talking about a 0.1% failure rate in the case of 1 million devices in 1,000 hours. So in this case, the difference between 149 and 151 is not that important. The most important thing is to keep your junction temperature as low as possible. The junction temperature, occasionally you have a discussion in the market. What is the best product, 150 degrees C or 175 degrees C? In a standard rectifier, definitely the junction temperature of 175 degrees C is better than 150 degrees C. In a Schottky diode, it may just reflect a different technology. The leakage current in a datasheet, is usually set at 1 to 5 microamp for rectifiers. But these standards are usually 30 to 50 years old. People had different ideas then about what reliability was all about. Normally, the leakage current of a rectifier, is around 100 nanoamp. Depends a little bit on the die size. Some would be 50, some 150. So you see that the real leakage current is actually quite far away from the actual test value. So sometimes you see discussions over the TJ rating of 100 and 175 degrees C. How, if I am comparing data sheets or don't know the supplier, do I know if this is true or not? In this case, actually, I would encourage you to look at the high temperature graphs. If somebody specifies their junction temperature at 150 or 175 degrees C, they really should have a lower leakage currents at the higher temperature. And you can compare those data, usually available in the data sheet, to see if they really are, there really is an improvement. Now we're going to the standard specifications, and this is what you usually get in your datasheet. You get your VF spec, different testing specs and different typical values. You get your leakage currents, and you also get your junction capacitance, and usually specified at 125 degrees C. What can we learn here from these data? They're pretty simple to understand, and it's pretty straightforward to interpret and compare, we think. Well, actually, rectifiers are temperature-driven devices. So the most important formula about a rectifier is that the TJ equals the ambient temperature plus the power dissipation multiplied by the thermal resistance. If you ignore the leakage current, your power dissipation is only the forward voltage and the forward losses, which is the IF multiplied by the VF. Now, if you look at this temperature, you can easily see that if you're a marketing person, you can actually change the current rating by changing the thermal resistance in the measurement, in the testing conditions. So if you look at the curves here, at the bottom right-hand side of the corner, of the slide, which looks like a typical rectifier datasheet, the people actually that determine these curves or make these curves, first and for all, they can adjust the slope, they can adjust the thermal resistance, and secondly, they can adjust the derating point. Those 2 points are chosen by marketing. So if you start using current rating to compare to rectifiers, like a 5 amp rectifier has to be a 5 amp rectifier, you can get some nasty surprises. You should really look at other things, and that's why we're going to the next slide. You should really look at these VF curves. These actually you cannot manipulate. If somebody does a good job or a decent job, measuring the VF over with the currents, and watch out with the VF measurements at very low currents, but the ones at 1 amp or 2 amps should be accurate. You can compare actually apples to apples when looking at this curve. So this is the way, or this is the main comparison point to see to check the die size of various suppliers. We should also point out that in many cases, just one wafer source is actually used to make different voltages. So the 100 volt parts and the 1000 volt parts are actually using the same wafer source, or they say wafer die size. So they actually have the same characteristics in forward direction. You can check this in the datasheet if you see that the VF spec is the same for all voltages, if the surge current is the same for all voltages, and the third indication you have sometimes of the die size is the junction capacitance. If those three things are the same for all voltages, then you can probably assume that one die source is used to create all the different part names. Two more data to look at in your datasheet. First and for all, the thermal resistance is given, usually as a junction to lead or junction to tie point, and then the next one, junction to ambient. The thermal resistance really resists of two parts. It's package related, or the junction to lead part, and then the second part is the contribution of the solder pad, which means it's determined by the designer. Now, these solder pad contribution dominates usually, is the most important part of the thermal resistance, and actually can vary a lot. The biggest variation is, for example, people like to give a very small recommended solder pads, like 1 millimeter by 1 millimeter or smaller. So you get the impression that the component will not take up a lot of PCB space, but then the thermal resistance is determined or measured using 5 millimeter by 5 millimeter solder pads, which is sometimes bigger than the package itself. So this is one area where you really have to be careful about. Most of the time, it's probably fair to say that datasheet values on thermal resistance tend to be rather optimistic. To make the part look more attractive to the designer, it can theoretically then handle more current, but it's not really. That's not really the case. You just need to compare the VF curves, as we said before. And there's a list of all different potential substrate and all potential ways to improve the thermal resistance. You just have to make sure you're comparing apples to apples, and it is still the best thing is still to compare the VF curves and sometimes the junction to lead value in the datasheet. Another thing that I wouldn't compare, or this is the one I am most worried about or not convinced about, is avalanche ratings in rectifier datasheets. They are a sign of robustness, so there's nothing wrong with them. If you use avalanche testing, then you weed out some parts with a poor characteristic. So there's nothing theoretically wrong with that thing, with that parameter. But if you actually use it, and if your design does use avalanche, then be aware that most avalanche pulses are single events, and you may have repetitive events, so you have a bigger power dissipation. And here, actually, it is really difficult to compare apples to apples. You're really going to have to use it in the field with tens of thousands of pieces to see if you have a significant change in your field failure rate, yes or no. So avalanche ratings are critical and tricky to compare. That is for higher voltage rectifiers. Lower voltage, Schottky have specific mechanisms to protect against avalanche, and these components are completely different from, for example, MOSFETs. MOSFETs have bulk breakdown, so the whole die helps you dissipating the power, whereas sometimes rectifier all the energy flows on the edge of the die, and it is definitely less robust. So this is some of the things you can compare and see in your data sheet. The next step we're doing is we're actually going to see what can you not see in your data sheet. What is hidden there? The first three things I think everybody will be familiar with. You have to test the efficiency in your design, test the EMI, and you better also check the junction or the case temperature with a camera to compare two components. So that's straightforward. For the other parts, the other invisible parts in the datasheet, I would like to go from the bottom to the top. So material differences and construction differences, that's quite important for bridge rectifiers, for example. Temperature cycling, differences in back-end assembly methods, reliability differences in front-end manufacturing methods. So those are things that you may want to discuss with your supplier. Different distributions, we're going to have a specific slide discussing that in detail. Different process technologies should be clear for everybody that makes a difference. A lot of rectifiers say GPP or glass passivated pellet, that stands for, but not every glass passivation process is similar to another one. And the most important, or the biggest surprises come from different test programs and different quality testing used by various semiconductor suppliers. And that's what we're going to show actually in the next slide. We mentioned this before, actually, right? The leakage current of a rectifier is about 100 microamp, and the datasheet spec is like 1 microamp or 5 microamp. So there's a huge gap between actually the distribution and what the USL is the upper spec limit. Now, what happens is that the devices that are outside the natural distribution, let's say 200, 300, 500 microamp, are probably devices with small cracks or difficult problems with the passivation. So actually, those are products that have potential reliability problems. That's why for rectifiers, we use something called PAT, or part average testing, where we align the test specification on IR with the normal distribution, not with the datasheet values. Some suppliers do that, other suppliers don't do that. So this is actually where you can get the biggest surprise if you switch from one supplier that does that and to another one that doesn't do that. The Chinese source, or even other renowned sources, may not all implement that. Taiwan Semiconductor implements this. So that's where you can get the biggest surprise when cross-surfacing rectifiers, is on this. Your field failures will increase depending on your temperature and how challenging how much you challenge the device. Your field failures may increase if you switch source. So this is one of the more hidden issues when changing rectifiers or cross-surfacing rectifiers. The next slide actually is made by my colleagues that works in quality. And it tells you a little bit of difference between automotive and non-automotive parts. I think it's probably fair to say that most of these differences are not going to influence the average design engineer. So, you're looking at things like man operators and rework, that type of stuff. This is all that professional auditors will verify to make sure that the process is under control and that you have a good strategy towards zero defects. I would, however, come to two more points on this slide. One is on CPKs. An average process has a CPK of 1.33. An automotive process needs a CPK of 1.67. This doesn't happen so much with standard rectifiers, but it handles quite often with Schottky specs. That means if you have the same product with the same distribution, you can actually, for a commercial part, have a better VF. You can have a VF of 0.52 instead of 0.55 in the case of a Schottky diode. And the automotive parts, with its tougher CPK requirements, may need actually a slightly higher VF spec to meet them. So what happens in this case, some people say, oh, this commercial part is actually better than the automotive part. No, it isn't, because it will have less losses and a better efficiency. Again, you need to look at the typical VF curves to actually compare those products. Automotive and non-automotive parts have different PAT testing, also part average testing specs. So this is one of the other differences, but both actually at Taiwan Semiconductor products actually have this available in the final test programs. We're going to actually have a very quick and simple summary. If you're cross-referencing standard rectifiers, actually, I don't want to make it more difficult than it is, or that make it sound very difficult or something like that. Actually, it's not that complex if you know some of the pitfalls or some of the problems you may have. If you have a conservative design, let's say you limit your PCB temperature to 90 degrees C, and you derate well, let's say you derate 20% on the breakdown voltage, and also you derate well on the surge current, the other absolute maximum value rate, then in that case you are probably safe. However, there are lots of people that have higher temperatures and are rather marginal on the datasheet spec. In that case, you should really take a lot of care and should be not only test the device, but also think about it. What will happen in volume? How will the new supplier impact the volume, shipments, and job volume performance of my design? So that more or less summarizes or talks about standard rectifiers. Now we have a lot of more rectifiers in our portfolio. The first one we're going to go to is the fast recovery or the fast efficient rectifiers. I'm starting with an oddity, which is the definition of TRR. Why is the definition or the test condition of TRR so strange? Well, test machines were developed like 30 or 40 years ago, and they're still used at the moment. So you have these data sheets, or some of them are very old, or traditions are very old, and actually people started copying it and still using those data sheets, and that's why you have actually currently a TRR test circuit that is actually no link to the real world and probably does not reflect what is going on in your circuit. So this is something you need to remember. So that's why you would also need to test this, of course, really in what happens in your circuit. These test conditions are, of course, what happened 30 years ago or 40 years ago. People were switching at 16 kilohertz, and usually most of the topologies were zero current switching. So the device was turned off when the current was at zero. So actually, this test circuit did well. It was okay, and nobody really bothered about it, and that's fine. At the moment, however, hard switching is becoming more and more prevalent, and in this condition, of course, this test circuit is completely inadequate. TRR is also not the most important parameter in a hard switching circuit. The losses are more determined by QRR and the peak reverse current. So here, the slide, actually, the print is a little bit small print here. That's, I guess, deliberate. So when you look at TRR definitions, you actually need to look at the small print of each device, because everybody may do it a little bit differently. But I would like to say in general that if the forward current and the DIDF dt ratio, the speed at which you turn off the forward current, unless they are the same, you cannot compare to TRR or QRR values of a rectifier. They need to be the same to have a meaningful comparison. If they are not, you need to test. Other things, of course, fast, efficient rectifier. What is important is they determine the EMI behavior. It is a very critical parameter. Sometimes softness is defined as the ratio of TB over TA, meaning the second half of the recovery slope is larger than the first half, and that's usually considered a soft part. But, so you need to test anyway the EMI, because no two fast recovery rectifiers are the same. Also, what you need to understand is that QRR and IRRM and also the TB over TA ratio are actually temperature dependent. So you need to test them at your worst case condition to really make sure that you have a adequate comparison between two suppliers. So this is something that is difficult to do just based upon the data sheet. Two more technology inputs for people that are working with these products. The low voltage FERs, those are usually products up to, let's say, 200 volts, can be made with epitaxial wafers or non-epitaxial wafers. With the epitaxial wafers having a much better VF, and occasionally also a better TRR. There is, of course, a cost penalty with these epitaxial wafers. So that's where sometimes cross-referencing becomes a little bit trickier to do. The second one, of course, is that the recovery behavior is determined by the amount of lifetime killing material in the rectifier. For example, how much platinum you had. So everybody has their own recipes. Some people add a bit more, some people add a bit less. So if you add more, the TRR goes down, but the VF goes up a little bit. So that's why there's going to be always minor differences between two suppliers of these products. Next online is bridge rectifiers. Again, this is easy. The data sheets are very easy to compare, and they follow the same rules as standard rectifiers. However, here this is still a manual process, so people have different constructions or methods. So you want to check the temperature profiles with an IR camera. Below that, you can see at the bottom, you can see a slide where we made an improvement in our packages for onboard chargers, where the temperature is more equal throughout the package by making the lead more symmetric. Here with bridge rectifiers, there's also a price war going on. So here die size is very important. It's very important to compare the die size. A lot of them are heat sinked. So people say, we can shrink the die size 10% and nobody won't notice. This can be noticed by comparing IFSM data, search current data, and you still need to look at the pictures or take the IR camera out and actually measure your temperature. It's a manual process, so there may be quality difference between suppliers. And the other thing here that we usually forget when we are cross-referencing rectifiers is molding compounds and humidity testing. A lot of, or sometimes in industrial application, let's say a water pump or anything else like that, there is a high humidity, and actually the difference in molding compound can have a significant impact on the field failure rate. So here you want to discuss reliability testing with your supplier before you switch, I think. Schottky diodes, how to cross-reference a Schottky diode. This is not so easy. This is the most difficult part to cross-reference. First of all, you match the breakdown voltage. But then you'd say the next step you could do is you're going to match the maximum junction temperature, 150 or 175 degrees C. But this is not so easy because these things are determined a little bit by marketing convention. You could say that some, depending on the percentage of silicide in the barrier material, you would say that some products would be 152 degrees C, 158 degrees C, 169 degrees C, 178 degrees C. So actually this is not practical. So marketing people make them either 150 or 178. But that does not mean that all these products are the same. They simply are not. Each of these Schottky diodes from different suppliers will have different VF and leakage current curves. So in the case, of course, of a Schottky rectifier, the power dissipations are determined not just by the forward losses, but also by the reverse losses. Let's say if you put 80 volts over a 5 milliamp leakage current for a typical Schottky diode, not even making it too hot, then you can see also there's 400 milliwatt there. So that's pretty substantial. You cannot ignore that. So if you are going to cross-reference a Schottky diode, you do not only compare the typical VF curves, but you also need to compare the typical leakage current curves. And you also have to watch out because making high temperature leakage curves is a tedious job. So suppliers have thousands of data sheet, and maybe not all Schottky data sheet high current leakage graphs in the industry are correct. So you're probably going to have to measure it yourself in your own circuit to make sure that you're comparing apples to apples in your application. The first formula here, there is the formula for the terminal runaway point. This is different from every Schottky device. Also note that it is dependent actually on the terminal resistance. We are currently writing a white paper on the thermal runaway of Schottky diodes and quality of Schottky diodes and junction temperature. This is a subject of another set of webinars in 2 or 3 months' time. When you actually are changing Schottky diodes, you're also going to change the EMI because the capacitance is going to be different. Trickier these days if you're going to switch trench Schottky with planar Schottkys. Two different technologies are now used to manufacturing Schottky, and they are completely different. The trench Schottky is the newer technology. It has a better VF for a given die size or a lower IR for a given VF, so it is the better technology of the two, but it comes at a certain wafer complexity penalty or price penalty sometimes. However, you need to also look at the trench Schottky as a higher capacitance, which may increase losses, but may also reduce the EMI. So both products are going to behave completely differently in your circuit, and if you're replacing one by the other, you are actually really making a new design rather than just cross-referencing parts. So in this case, you really have to watch out and be very careful. We're going on with TVS diodes, or transient voltage suppressors. These are actually also easy to cross-reference. A 400 watt device or a 600 watt device is a 600 watt device from everybody. Every supplier tests it 100%, and the pulse can be guaranteed in the datasheet, so you can have no worries actually replacing one with the other. Also the pulses are very well normed, so you shouldn't worry about too much when you're cross-referencing TVS diodes. Sometimes there's a complexity that some part names are actually using the breakdown voltage, and some part is actually using the standoff voltage or the working voltage. So this can be a nuisance when you are cross-referencing parts, but you should understand that these are just two different test programs. There's not essentially a difference between the two products. So when used as a protection element, the transient thermal impedance is the key factor. The pulses are shorter than 1.5 milliseconds, so the die size is the key factor. So the most problems come sometimes that, for the CE sign, you have a fixed bill of material, and then, you need to qualify again for the CE sign with the new component, which can be a nuisance, but it's simple to do if you want to. So what issues can you get with transient voltage suppressor? First and for all, the lightning strike does whatever it wants to, so you can norm it, but if it can still be contain much more energy. The norm actually covers only 99% plus of all the lightning strikes, but some of them can be slightly more powerful. This is something you'll see when you use the device externally in industrial applications. There you will see that a different supplier with different die sizes will have a different robustness and may have a different field return ratio. So you can only find that out, or if you are using your product outside, you may also want to check the die size of the different suppliers and how much margin you have. And of course, not all TVS diodes are used as transient voltage protections, or some of them are used as snubbers or as high power ZENERs. In that case, actually the die size and the thermal performance is important, and you do need to test the temperature in the circuit itself before you can actually change the different component. The maximum TJ here is slightly less important, because in a single pulse event, actually in a lightning strikes, the maximum TJ can be exceeded. It's a search to fail test, so the device either survives or doesn't survive. The TJ max is not the issue here; it is exceeded. We're going to the end here. Small signal products are, you can use surge engines to second source them, whatever it is. They are usually the same thing. The only thing that I would like to point here is where you could go wrong is that ZENERs, or sometimes small signal transistors, can have manipulated power ratings by mounting them on substrate with a much more lower thermal resistance. I'll give you, or ceramic substrate even. I'll give you an example of that. When there are pulses, the internal construction becomes important. I'll give you also an example of that. So sometimes ZENERs are used in pulsed environments, or small signal diode are followed by a capacitance. In that case, the internal construction can give failures, and two different suppliers may actually not perform the same. Examples of that are, normally we are, very, kind to each other, and we talk about competitor A or B, things like that. This is competitor Xperia, because they do this all the time. All of a sudden, your 300 milliamp, or 300 milliwatt small signal transistor becomes a 1.5 watt animal or something like that by putting it on substrates or mounting pads which are 10 times the size of the transistor itself, or 50 times the size, and on unrealistic PCBs. So watch out with these small signal things. These things happen, and it makes second sourcing sometimes difficult, but the power rating sometimes is exaggerated by some people in the industry. So you may want to look at the small print in this case again. The other one area where you could go wrong is the construction method. I'm just going to look at the pictures here. You can study the difference between a ZENER and a TVS yourself if you feel like it. But the left one is a glass diode. And what happens is the chip is contacted between the two copper slugs, and then it is a vacuum, compacts it. The issue is the chip is contacted with the copper slug is what they call a pressure contact. It's not soldered. Let's say an SMA package or other bigger packages, things that they are soldered. This goes completely wrong, or this soldering is a guarantee, for if a larger pulse happens. So ZENER diodes are okay if you're using as ZENERs, but if you start using them as, for example, overvoltage protection elements, you can go wrong and you can have field failures, or the feed failures may actually be completely different between two suppliers because of their internal construction. So this actually you need to test and also ask the supplier what their construction is. Conclusions. Here we are. So when we compare datasheet, you have to be aware that they are not only technical documents, but that marketing people can have an influence too. What happens a lot is that competitor X has a very popular product in the market. Competitor Y decides to copy it. They have just the marketing people make just the same datasheet, so everything looks the same to you as the designer. But that doesn't mean that they have the same process, the same testing program, and that everything in the background is the same. It isn't. Testing is necessary when the device is used to the datasheet limit, or when the ambient temperature or power dissipation is high. If you have conservative designs, your testing should be limited or can be quite modest and things like that. If you're actually using it at high temperature and to the end, you may want to test extensively, not just into one or two parts. You may want to talk to your supplier about the processes and technology used to make the product, and also test programs. Especially if you're going to use the product in high volume, if you use 1 million pieces, and if you really want to have 0 defects. If you're using 10,000 pieces, you may not notice the difference, but if you are really in high volume applications, you should try to understand these things. So follow some of the basic rules outlined in the white paper, and you will safely be able to cross-reference rectifiers. So I hope I gave you all the possible information you need to cross-reference rectifiers. I am now open for your questions. And as I said before, please note that you can actually download on the event board the presentation. Thank you for your attention.